Hello and welcome to Chapter 10, Vagabonds of the Solar System, where we are going to talk about dwarf planets, meteorites, comets, and any other objects which are not a planet or a moon that we have discussed so far. Now that we have explored the properties of the planets and their moons, we finished studying the objects orbiting the Sun in this chapter. Recall that astronomers have several overlapping ways of classifying the bodies orbiting the Sun. To briefly review, recall that a planet is a celestial body that is 1. In orbit around the Sun, 2. Has sufficient mass for its self-gravity to pull itself into a nearly spherical shape, and 3. Also has enough mass for its gravitational force to clear its neighborhood of orbiting space debris. A dwarf planet satisfies 1 and 2, but does not have enough gravity to clear its orbital neighborhood of debris. All objects in the solar system that are not planets, dwarf planets, or moons are debris called small solar system bodies, or SSSBs. So far, Pluto, Ceres, Eris, Makemake, and Haumea have earned the title of dwarf planets. Haumea has a peculiar shape for a dwarf planet. As you will see, it is distinctly egg-shaped rather than being uniformly wider at its equator than at its poles. This peculiar shape is believed to be due to Haumea's exceptionally rapid rotation. Indeed, its motion is analogous to an egg spinning on a table. The latter 3 bodies were discovered in 2005. 6 more candidate dwarf bodies are being studied. Bear in mind that the properties of more solar system objects are pinned down. The definitions of dwarf planets and SSSBs may be refined. Pluto was discovered in 1930 by Clyde Tombaugh, who found it by examining photographic plates showing that it moved among the background stars from night to night. The only spacecraft to visit it, New Horizons, passed closest to it on July 14, 2015. The images sent back to us of Pluto and its moons revealed worlds very different from all of the others we have discussed so far. Where Pluto has this very nice images that were released in 2015 and has this very interesting heart-shaped feature that we will get into discussing a little bit more in detail. More than 1,000 craters on Pluto have been cataloged. Most are worn down or partially destroyed by erosion. The left side of the wide heart-shaped region called Sputnik Planitia or Planitia is nearly free of craters. To the left of this region are features consistent with the surface having fractured in the past. Astronomers propose that when Pluto was young, the left half of the heart-shaped region had mountains built up on it atop an icy interior. The weight of that surface rock eventually crushed the ices below it, which caused the mountains to sink, just as would happen if you walked on thin ice here on Earth. The formation of the right half of the heart is still to be studied. A New Horizons image indicates the presence of cryovolcanoes, volcanoes that emit a slurry of water, nitrogen, methane, or ammonia rather than molten rock. Unlike the planets, Pluto's orbital eccentricity of 0.25 is so great that it is sometimes closer to the Sun than Neptune, as it was from 1979 to 1999. Pluto is now farther away from the Sun than Neptune and will continue to be so until April 5, 2231. Pluto's orbital inclination, the tilt of its orbit with respect to the plane of the ecliptic, is just over 17 degrees, far greater than that of any planet. Charon. Little was known about Pluto for half a century until astronomers noticed that its image sometimes appeared oblong. This observation led to the discovery in 1978 of Pluto's largest moon, Charon. The mass of an object in space can only be determined directly from its gravitational attraction on another body. We know the mass of the Sun because we can determine the length of Earth's year. We know the mass of Mars because we can determine the periods of its moon, Phobos and Deimos. The mass of Pluto, 2.2 times 10 to the negative 3 mass of the Earth, was not known until the orbit of Charon was accurately determined in the early 1980s. In 2005, the Hubble Space Telescope detected 2 other moons orbiting Pluto, called Nix and Hydra. These moons are much smaller than Charon. The 4th and 5th known moons, Styx and Kerberos, were discovered in 2011 and 2012, respectively. Nix, Hydra, and Styx are very bright, suggesting that they are covered with layers of ice. Kerberos is as dark as charcoal. Styx and Kerberos are tumbling chaotically under the changing gravitational attraction of Pluto and Charon. Like Neptune's moon Triton, Pluto and Charon are probably both composed of nearly equal amounts of rock and ice. The surface of Pluto has 12 distinct regions, more large-scale features than any object in the solar system other than Earth. Such features on Earth include oceans and continents, while on Pluto they include regions dominated by rock, regions dominated by ice, major impact regions, and mountain ranges. One mountain range on Pluto extends as high as 3.5 kilometers, and because the area lacks nearby cratering that comes with age, the mountains are believed to be no more than 100 million years old. It remains to be determined how these mountains formed. On New Year's Day 1801, Sicilian astronomer Giuseppe Piazzi was carefully mapping faint stars in the constellation Taurus. He noticed a dim, previously uncharted star that shifted its position slightly over the next several nights. Uranus had been discovered in this way by William Herschel just 20 years before. Later that year, the orbit of Piazzi's object was determined to lie between Mars and Jupiter. At his request, it was named Ceres. Based on erroneous observations of its size, Ceres was initially catalogued as a planet. In 1855, further observations revealed that all of the then-known planets, Mercury, Venus, Mars, Jupiter, Saturn, and Uranus, were much larger than Ceres. We did not know Piazzi was the first astronomer to discover an asteroid. Ceres is spherical like the planets, but its diameter is a scant 940 kilometers, only 1/4 of the diameter of our moon. In 2006, it was classified as a dwarf planet. It was visited by the Dawn spacecraft, which orbited it from 2015 through 2018. Recent calculations suggest that, like other planets, Ceres is differentiated, containing a rocky core and clad in an icy outer shell. Salts, water, ice, and clays rich in ammonia have been detected on its surface. In 2016, Dawn also detected organic, carbon-based compounds there. These compounds are the building blocks of life, although no life is expected to exist on Ceres. Ceres also has a very thin atmosphere of water that waxes and wanes with solar activity. When the sun is particularly active, more particles streaming out of it strike Ceres' surface, releasing water from the ice there. That atmosphere dissipates within a week of when the sun's activity returns to normal. Eris was first observed in 2003, before the present definition of planets, dwarf planets, and SSSBs were established. The body is presently located 98 astronomical units from the Sun, 3 times larger out than Pluto. Further out than Pluto, rather. All bodies orbiting the Sun between Neptune are called trans-Neptunian objects, or TNO. Pluto, along with Eris, Makemake, and Haumea, are dwarf planets and TNMOs. Furthermore, the 558-year orbit of Eris is so eccentric that for part of its time, Eris is closer to the Sun than Pluto. Eris has a diameter of about 2,400 kilometers and is very bright, with an albedo of about 8.86. Observations suggest that 1/4 of this world is water ice, a greater volume than all the fresh water on Earth. A moon orbiting Eris named Dysnomia was discovered in 2005. The moon is about 300 kilometers across. Haumea, discovered in 2005, rotates once every 3 hours and 55 minutes. In other words, a day on Haumea is less than 4 hours long. It is likely that Haumea's rapid rotation is the result of it colliding with another body. Because of that rapid rotation, this world has distorted itself so that it looks like a watermelon. Haumea is a dwarf planet even though its rapid rotation deforms it from spherical, which calculations show it would be if it were not spinning. Its mass is about 1/3 that of Pluto. Haumea has 2 known moons, Hi'iaka and Namaka. They are named after Haumea's mythological daughters. Spectra of both moons reveal that, unlike the rest of the bodies observed in the outer solar system, their surfaces are made of almost pure water ice. In contrast, most objects have surfaces of rock and ice, where the ice often contains molecules other than water. Like Haumea, Hi'iaka is an exceptionally short rotational period. Astronomers had originally expected it to be in synchronous rotation around Haumea with a 49.5-day period, but observations revealed that Hi'iaka spins once every 9.8 hours. Besides having 2 moons, Haumea has a ring located 2287 kilometers from the center of the dwarf planet. The composition of the ring debris is still under investigation. Makemake, also discovered in 2005, rotates once every 7 hours and 45 minutes. It is about 3/4 the size of Pluto, and it orbits the Sun once every 310 years. Unlike the other Kuiper Belt dwarf planets, Makemake has no known moons. We know that the solar system formed from a rotating disk of gas and dust. The matter in the disk that had too much angular momentum to fall into the protosun coalesced at varying orbital distances into planetesimals. Many of these chunks of rock, metal, and ice eventually collided, forming the planets, dwarf planets, and larger moons of the solar system, as well as myriad pieces of dust, rock, and boulder-sized debris. Other chunks of rock, metal, and ice were captured whole by various planets as small, irregularly shaped moons like Phobos and Deimos are in orbit around Mars. Many planetesimals still orbit the Sun today in splendid isolation. These are the asteroids, sometimes called minor planets, not to be confused with dwarf planets. In 1802, less than 2 years after the asteroid, now called also a dwarf planet, Ceres was discovered, the German astronomer Heinrich Olbers observed another faint star-like object that moved against the background of stars. He called it Pallas, after the Greek goddess of wisdom. Like Ceres, Pallas orbits the Sun in a nearly circular path between the orbits of Mars and Jupiter. Pallas is even dimmer and smaller than Ceres and has a diameter of only 600 kilometers. Only 2 more of these asteroids, Juno and Vesta, were found until the mid-1800s, when telescopes improved. Astronomers then began to discover many more asteroids orbiting the Sun at distances from 2 to 3.5 AU between the orbits of Mars and Jupiter. This region of the solar system is now called the asteroid belt. Asteroids whose orbits lie entirely within this region are called belt asteroids. Asteroids were discovered one by one through the 19th century. The next real breakthrough came in 1891 when the German astronomer Max Wolf applied photographic techniques to asteroid searching. A total of 300 asteroids had been found up to that time, each painstakingly discovered by scrutinizing the skies for faint, uncharted stars whose positions shifted slowly from one night to the next. With the advent of astrophotography, however, the floodgates were open. Astronomers could simply aim a camera-equipped telescope at the stars and take long exposures, and an asteroid happened to be in the field of view. It left a distinctive trail on the photographic plate. Using this technique, Wolf alone discovered 228 asteroids. Records of all objects smaller than planets in our solar system are kept by the Minor Planet Center in Cambridge, Massachusetts. The center reports that as of July 20th, 2018, the existence of 779,736 asteroids has been confirmed, up from 508,765 on December 12, 2017. Based on these observations, we know that Ceres, the largest asteroid, alone accounts for about 30% of the mass of all known asteroids combined. Only 3 asteroids, Ceres, Vesta, and Pallas, have diameters greater than 300 kilometers. Indeed, the number of asteroids increases dramatically with decreasing size. Only 41 asteroids have diameters between 200 and 300 kilometers. 250 more are bigger than 100 kilometers across, and there are thought to be tens of millions that are less than 1 kilometer across. The NICE model of how the solar system formed predicts that all the debris that formed above the solar system was initially orbiting in the same direction, namely counterclockwise, as seen from above Earth's North Pole. As a result, all the large objects such as planets, moons, and dwarf planets are orbiting in that direction today. However, a small but growing number of asteroids have been observed orbiting in this opposite direction, namely clockwise, as seen from above our North Pole. Astronomers estimate that about 0.01% of asteroids have these retrograde orbits. One recently discovered example, labeled 2015 BZ509, is in nearly the same orbit as Jupiter, albeit in the opposite direction. One hypothesis is that this asteroid and perhaps others in these retrograde orbits came from other star systems and were captured by the gravitational attraction of the giant planets. The NICE model explains that most of the debris in the present area of the asteroid belt was sent out there by the migration of young Jupiter through this region, going both inward and outward again, as discussed in section 6.2. If all of the present asteroids were collected into a single body, it would have the diameter of only 1,500 kilometers, or 12% of Earth's diameter. This is less than 2/3 of the diameter in Pluto and half the diameter of our moon. Like Pluto, such a body would not have enough gravitational attraction to clear the space around it or other bodies. Therefore, a single body that contains the mass of all the asteroids also would not qualify as a planet. In 1867, the American astronomer Daniel Kirkwood called attention to gaps in the asteroid belt. These features, called Kirkwood gaps, show the influence of Jupiter's gravitational attraction there today. In Figure 1014, which is the next slide, a graph of asteroid orbital periods has gaps at simple fractions of Jupiter's orbital period. The gravitational pull of Jupiter created these empty regions by giving objects in them periodic reinforcement tubs that pulled the orbiting bodies into different orbits. The effect is analogous to the gravitational resonance of Mimas created the Cassini division in Saturn's rings. Recall that, according to Kepler's third law, the period of an object is dependent on the semi-major axis that it has in its orbit around the Sun. What this means is that with objects in the asteroid belt that are going to come into contact with Jupiter, meaning that, say, every 3 times they orbit, Jupiter orbits once, or every 5 times they orbit, Jupiter orbits twice, or something like that, where they constantly come very close to Jupiter. That means that there's going to be a push or a pull as it comes close to Jupiter over and over again, which is going to push it out of its current position. And because these periods are dependent on the semi-major axis, that means that there are areas in the semi-major axis or radii out from the Sun that because the periods are synced up with Jupiter, are going to be bereft of asteroids, which is a really neat application of Kepler's third law that is just demonstrating the validity of it and demonstrating something really interesting that happens because of it. It is likely that the asteroid belt contains tens of millions of asteroids, yet the typical separation between neighboring asteroids is an impressive 1 million kilometers. Despite the large average separation between asteroids, the gravitational influence of Mars and Jupiter have sent some asteroids smashing into each other at various times over the past 4.6 billion years. In 2010, astronomers observed 2 such events. Typical collision velocities are estimated to be 3,600 to 18,000 kilometers per hour, which is more than sufficient to shatter rock. In some collisions, the resulting fragments may not have enough speed to escape from one another's gravitational attraction, and they reassemble. The asteroid Totatus appears to be composed of 2 similarly sized pieces connected to each other, as do the asteroids Castalia and Itokawa. These bodies are therefore likely to have either been broken apart as a result of the collision and then drifted back together, or they may be pieces from 2 different asteroids that drifted together. As seen here. Alternatively, several large fragments such as Ida and Dactyl may end up orbiting each other. Dactyl is a pockmarked asteroid some 1.5 kilometers in diameter that orbits Ida at a distance of 100 kilometers. Petit Prince is a satellite of Eugenia. Petit Prince is 13 kilometers across, orbiting 1,200 kilometers from the larger body. Asteroid 87 Sylvia has 2 known satellites named Romulus and Remus. To date, 323 asteroid satellite systems have been observed, including several with 2 moons. I also want to talk about the name Petit Prince, which is in reference to the Eugenia's actual child, but is also a reference to the children's book Le Petit Prince, or The Little Prince, where the prince lives on an asteroid in the days when we were in the early 1900s, so in the days when we were still finding out a lot about them. Despite being composed primarily of rock and metal, some asteroids are weakly bound agglomerations of this material. In 2013 and 2014, telescopes on Earth and the Hubble Space Telescope observed P2013 R3 break into pieces. It is unlikely that a collision caused this activity, A collision would send debris flying away at great speeds, but this asteroid's pieces are drifting apart at a leisurely 2 kilometers per hour, probably weakened by many small collisions over billions of years. Astronomers speculate that heating from the sun and the asteroid's rotation has finally caused it to fragment. Another curious asteroid phenomenon was also observed in 2013 when the Hubble Space Telescope imaged a rotating asteroid that periodically emitted 6 jets of gas and dust. When active, the streams appeared like the water from a rotating sprinkler. One possible explanation for these ejecta is that the asteroid is rotating so fast that it was having trouble staying together. As a result, the centrifugal force, outward force due to the rotation, could push some of its dust into space as jets. While Jupiter's gravitational pull clears out certain areas within the asteroid belt, it actually captures asteroids at 2 locations in the path of its own orbit. The gravitational forces of the Sun and Jupiter work together to hold asteroids in orbit at these locations, called stable Lagrange points, in honor of the French mathematician Joseph Lagrange, whose calculations explain them. One Lagrange point is located ahead of Jupiter and the other is behind. Other asteroids have highly elliptical orbits. Some of these pass through the inner regions of the solar system. The Amur asteroids cross Mars's orbit but do not get to as close to the Sun as Earth's orbit, whereas the Apollo asteroids do cross Earth's orbit. At least 8,180 Earth-crossing asteroids are known, several of which are pairs of asteroids that orbit each other. Not all of these Earth-crossing asteroids pose threats to Earth, but at least 1,472 of these are potentially hazardous asteroids that may someday strike Earth. Still, other asteroids have similarly elliptical orbits that extend from the asteroid belt out beyond the farthest reaches of Pluto's orbit. The proximity of asteroids and the promise of learning more about these ancient and extremely varied members of our solar system prompted NASA to send the Near-Earth Asteroid Rendezvous Shoemaker spacecraft to visit asteroids Matilde and Eros. JAXA, the Japanese space agency, sent the Hayabusa spacecraft to the asteroid Itokawa. While the spacecraft attempted to take samples, these maneuvers were only partially successful. The Hayabusa returned to Earth in June 2010 with its cargo. In November 2010, some of the dust particles it carried were confirmed to have come from the asteroid Itokawa. The dust particles had been exposed to space for only about 8 million years, suggesting that Itokawa had once been part of a larger body that recently came apart. Near Shoemaker revealed that Matilde is only 1.3 times denser than water and has an albedo of 0.04, making it darker than charcoal. This heavily cratered carbon-rich body therefore has only half the density of the other asteroids astronomers have studied, such as Ida. Eros is about 3 times as dense as water and rotates once every 5.25 hours. In February 2000, Near Shoemaker went into orbit around Eros, and for a year the spacecraft's cameras and other sensors sent back a wealth of information about it. Near Shoemaker also showed that Eros is a chunk of rock and metal. Whether that asteroid is solid or a collection of loosely held pieces is still under investigation. Analyzing Eros' spectra reveals that it is probably much the same as it was when it coalesced 4.6 billion years ago. Thus, it was never hot to separate rock from metal. Infrared observations reveal that, like our moon, Eros has a regolith. It is also has several substantial craters and is strewn with boulders. Astronomers infer from the lack of high crater walls that recent impacts have caused the asteroid to vibrate, collapsing earlier craters. On February 12, 2001, NASA engineers set Near Shoemaker onto Eros so gently that the spacecraft was able to transmit data after landing. Details of Eros as small as 1.4 meters across were imaged by the spacecraft. While asteroids consist primarily of rock and metal, other small solar system bodies contain large amounts of frozen water and ices of other compounds. We have seen in earlier chapters that water ice, along with carbon dioxide, methane, and ammonia ices, were locked up in planets and moons. Ices in the young solar system also condensed with smaller amounts of rocky and metallic debris into bodies that still remain in orbit around the Sun. These dirty snowballs in space are the comets. The vast majority of them in our solar system are located in the Kuiper Belt and the Oort cloud. Their are also hybrid objects orbiting the Sun in the outer solar systems called centaurs that have a roughly equal mix of rock and ice. Two centaurs, Chariklo and Chiron, are also observed to have rings of ice particles in orbit around them. The ring material may have been acquired when these bodies each passed near a planet with rings. Because of their low gravitational attraction, it is plausible that they also each have at least two moons that behave like the shepherd moons, like those orbiting the vicinity of Saturn's F ring. These moons orbiting centaurs would help keep the debris in orbit. Comets and centaurs are named after their discoverers whenever possible. For example, Comet Shoemaker-Levy 9 was the ninth comet discovered by Caroline and Eugene Shoemaker, and separately but simultaneously by David Levy. Today, with large teams of astronomers using sophisticated observing equipment to locate comets, it is sometimes impossible to attribute their discoveries to just a few team members. Comets found under these circumstances are named after the team or the research program that finds them. In 2001, astronomers were able to measure the temperature at which ammonia ice formed in Comet Linear, named after the Lincoln Near-Earth Asteroid Program which discovered it. This temperature determines the ammonia's solid structure, and by determining the structure of the ammonia in Comet Linear, scientists were able to calculate the temperatures when it formed and therefore how far the comet was from the Sun at the time. The comet coalesced between the present orbits of Saturn and Uranus. The solar system is believed to contain two reservoirs of comets and centaurs, the Kuiper Belt and the Oort cloud, from which some of these bodies are nudged toward the intersolar system by near misses between them. Indeed, such near misses are the primary source of the comets that enter the realm of the planets. The Kuiper Belt is centered on the plane of the ecliptic. Its main body orbits and extends out from about 30 to 55 AU from the Sun. Astronomers believe that most comets entering this inner solar system come from the Kuiper Belt because most of those comets have orbits relatively close to the plane of the ecliptic. If most comets came from the spherical Oort cloud, the planes of their orbits when near the Sun would be random and with most located far from the plane of the ecliptic. The Kuiper Belt objects were first discovered in 1992, and they fall into two groups. Those with roughly circular orbits are called classical KBLs and found between 30 and 50 AU from the Sun. The second group, called scattered KBLs, have more elliptical orbits and range from 35 AU to at least 200 AU from the Sun. More than 50 or 1,500 Kuiper Belt objects have been observed. Although most of the observed KBLs are tens of kilometers across, astronomers have also begun to observe some KBLs only 10 to 100 meters in diameter. Based on this latter astronomy or observations, astronomers estimate that such objects exist out there. The first classical KBL discovered in 1992 was named Albion. And then this diagram gives us an idea of the distribution of SSSBs throughout the solar system. At least 1% of the KBLs are orbiting pairs, including Quaoar, which is 1,100 kilometers apart across, some 150 kilometers larger than Ceres, or just under half the size of Pluto. At least 122 of the KBLs orbiting the Sun at the same region as Pluto. These latter bodies are also called Plutinos. The period of Neptune's orbit around the Sun is 2/3 as long as the orbital period of Pluto and the Plutinos. Indeed, it appears that Pluto and the Plutinos were forced into their present orbit by Neptune's gravity. Thus, astronomers say that Plutinos are locked in a 2 to 3 resonance with Neptune. The vast majority of comets are believed to lie even farther from the Sun. Unlike the Kuiper Belt comets and the rest of the solar system, these bodies are believed to have a spherical distribution around the Sun called the Oort cloud, named after the Dutch astronomer Jan Oort, who first proposed its existence in the 1950s. The Oort cloud extends roughly 5,000 to 100,000 AUs from the Sun. In other words, the outer edge of the Oort cloud is some 2/5 of the distance to the star nearest to the solar system. It is estimated to contain between 0.01 and 2 trillion objects thought to be mostly composed of rock and ice. Most comets have orbits sufficiently circular that they never even get close as Pluto is to the Sun. However, occasionally a near miss between two comet nuclei nudges a distant comet towards the inner solar system. As a result of its inward plunge, comets from the Oort cloud, like Comet Hale-Bopp and Comet Hyakutake, have highly elliptical, parabolic, or even slightly hyperbolic orbits. Often, Oort clouds comets also have orbits that are highly tilted, even perpendicular to the plane of the ecliptic. An especially intriguing result of the Rosetta observations concerns the origin of water on Earth. As noted in Section 7.1, a sizable fraction of Earth's water is believed to have been deposited here as a result of comet impacts. However, water can have any of three kinds of hydrogen atoms called different isotopes. Isolated protons denoted H, or a combined proton and a neutron denoted D, and called deuterium, or a proton with two neutrons denoted T, and called tritium. Most of our water has been isolated proton version of hydrogen, H. We can calculate the ratio of, for example, D to H denoted as D/H for any sample of water. If water came from comets, we would expect the D to H ratio of Earth's water and the water of comets to essentially be the same. However, the D/H ratio in the Churyumov-Gerasimenko is 3 times higher than the water we drink, meaning that the water did not come from comets like it. On the other hand, Comet Hartley 2 was observed in 2012 to have the same D to H ratio as Earth. One possible explanation astronomers and geologists are exploring is that water came from a family of comets with the same D to H ratio as we have on Earth, but not from the other comets with this different ratio. To better determine the composition of the gas emitted by comets, the Stardust probe visited Comet Wild 2, where it collected samples and returned them to Earth in 2006. Among the most interesting discoveries was the presence of amino acids, the building blocks of protein upon which terrestrial life is based. Comet Wild 2 itself showed many unexpected features, including towering spires, many craters and cliffs, and more than 24 jets, rather than the 2 or 3 jets seen on other comets. As the comet nucleus comes within 20 AU of the Sun, solar radiation begins to sublimate, change directly from solid to gas, the ices on its surface. The liberated gases from an atmosphere, or coma, around the nucleus. Because the coma scatters sunlight, it appears as a fuzzy, luminous ball. The largest comet ever measured was that on Comet Holmes, which in 2007 near its perihelion was 1.4 kilometers across, larger than the Sun. Not visible to the human eye is the hydrogen envelope, a sphere of tenuous gas surrounding the comet's nucleus and measuring as much as 20 million kilometers in diameter. The most visible and inspiring features of comets are their long, flowing, diaphanous tails. Comet tails develop from comet gases and dust pushed outward by radiation and particles from the Sun. Thus, comet tails do not trail behind the nucleus as the exhaust from a jet plane does in Earth's atmosphere. Rather, the comet's nucleus, the tails always point away from the Sun, regardless of the direction of the comet's motion. The implication that something from the Sun blows the comet's gases radial outward led Ludwig Biermann to predict the existence of the solar wind. This stream of particles from the Sun was actually discovered in 1962, a full decade after it was first predicted, by instruments on the spacecraft Mariner 2. In 2001, NASA launched the Genesis spacecraft, which collected pristine solar wind particles for 2.5 years. Although it crash-landed back on Earth in September 2004, some of the particles that it collected were salvaged in studies. From these, astronomers discovered that the chemistry of the Sun and the chemistry of Earth have important differences. In particular, the isotopes of oxygen and nitrogen are found in different amounts on the two worlds. For example, when comparing the amount of 14 nitrogen, or nitrogen-14 nitrogen with 7 neutrons, and nitrogen-15 nitrogen with 8 neutrons, Earth has 40% more than does the Sun. The reason for this and other chemical differences are now being studied. We see this interesting pattern where the comet comes from the left, down, and then goes back up to the right, where at any given point, instead of trailing like a jet does, you see the two tails of the comet pointing in directions opposing the sun. This is caused by the solar winds. Outflowing particles and radiation from the sun produce two comet tails: a gas or ion or plasma tail and a dust tail. Positively charged ions, atoms missing one or more electrons, from the comet are swept directly away from the sun by the solar wind to form the gas tail. Gas tails are composed primarily of water, carbon monoxide, carbon dioxide, methanol, and ammonia. Such tails appear blue because carbon monoxide ions in the gas strongly scatter blue light. The relative straight gas tail can change dramatically from night to night. These changes occur because the solar wind that pushes the gases changes rapidly, and the gases themselves are very light and easily moved out, like the smoke from a fire. The dust tail is formed when sunlight strikes dust particles that have been freed from the comet's evaporating nucleus. Light exerts pressure on any object that absorbs or scatters it. While this pressure, called radiation pressure or photon pressure, is quite weak, fine-grained dust particles in a comet's are sufficiently light to be pushed away from the vicinity of the comet, thus producing a dust tail. The dust tail is often white or light gray. The dust particles are massive enough to not to flow straight away from the sun. Rather, the dust tail arches in a path that lies between the gas tail and the direction from which the comet came. Even though gas trails of most comets appear significantly brighter and often longer than dust tails and other rocky debris, observation reveals that about 3 times as much mass leaves a typical comet in the form of dust and rocks than leaves as gas. Comets cannot survive an infinite number of passages near the sun. The comet's first close encounter causes it to lose a large amount of its surface ice. In doing so, the dust it contains becomes a more significant part of its surface. The dust helps insulate it, reducing the amount of ice and dust the comet loses in subsequent close passages near the sun. A typical comet is estimated to make between 60 and 100 passages to perihelion, closest approach to the sun, before losing all of its ice. Because the rock and metal debris in a comet are held together by the ices in which they are embedded, when the ices are gone, the solid pieces drift apart, meaning many of them remain in orbit around the sun. Halley's Comet has been seen at least 27 times, meaning that it has fewer than 73 more close passes to the sun before it dissipates. Because it returns every 76 years ago, it will survive about 73 times 76 is 548 more years. A comet can also be torn apart when it comes too close to a planet or a sun, or it can be destroyed completely by striking a planet, a moon, or the sun. A spectacular example was comet Shoemaker-Levy. That comet fragmented under the tidal force of Jupiter in 1992. 2 years later, with the world's astronomers watching carefully, the pieces returned and struck the planet. Impacts on Jupiter by single objects were also observed in 2009 and 2012. Comets occasionally lose mass quickly by ejecting it in bursts. Several times, starting in September 1995, astronomers observed comet Hale-Bopp eject 7 to 10 times more mass than usual. Astronomers think that these events result from surface ice and dust being heated by the sun and then being rapidly ejected from the local region on the comet's surface called a vent. Hale-Bopp rotates with a period of about 12 hours. The ejected matter therefore formed a pinwheel-shaped distribution spiraling through the comet's nucleus at a speed of 109 kilometers per hour. Although the ejected matter did not represent a significant fraction of the comet's mass, its light reflecting dust made it look like a huge comet fragment. As noted earlier, asteroids occasionally collide with each other, sending fragments into interplanetary space. These smaller pieces, along with the rocky and metallic debris from evaporating comets and material that never coalesced into larger particles, still orbiting the sun. Meteoroids are rocky and metallic debris smaller than asteroids that are scattered through the solar system. Although no official size standard distinguishes the two, meteoroids are no more than about 10 meters across, and the vast majority of them are smaller than 1 millimeter. Meteors and meteoroids that are being vaporized Meteors are meteoroids that are being vaporized by the atmosphere. Meteorites are remnants of meteoroids that land intact. By studying the chemistry of various asteroids, astronomers are now beginning to identify which ones were the origins for other asteroids and for meteoroids. For example, the asteroid Brel is a piece of debris 2 kilometers long that was blasted off the 500-kilometer diameter asteroid Vesta. Passing meteoroids are often pulled by gravity toward Earth. As they move through our atmosphere, they compress and heat the gases in front of them so much that the surrounding air glows. The glowing gas, accompanied by vaporized pieces of infalling matter, creates the trail we see, and the meteoroid becomes a meteor. Common names for these dramatic streaks of light flashing across the sky include shooting stars, fireballs, and bolides. Fireballs are meteors that are at least as bright as Venus. Bolides are bright meteors that explode in the air. Therefore, shooting stars are not stars of any kind or dying stars. A spectacular bolide estimated to have been 17 to 20 meters across was seen passing over Chelyabinsk, Russia on February 15, 2013. Moving faster than the speed of sound, the sonic boom it created broke innumerable windows. The bolide then exploded at an altitude of about 32 kilometers above Lake Cherbarko. Had it exploded over the city, the debris that rained down would likely have killed people. As it happened, no one was killed in the event, though a reported 1,600 injuries were caused by windows shattered in the explosion, among other causes. 105 years before the meteorite in Chelyabinsk, at 7:14 a.m. local time on June 30th, 1908, a much more spectacular explosion occurred over Russia, this one over the Tunguska region of Siberia. The blast, comparable to a nuclear detonation of several megatons, knocked a man off his porch some 60 kilometers away and was audible at a distance of more than 1,000 kilometers. Millions of tons of dust were injected into the atmosphere, darkening the sky as far away as California. Preoccupied with wars, along with political and economic upheaval, neither Russia nor its successor, the Soviet Union, sent a scientific expedition out to the site until 1927. At that time, Soviet researchers found that trees had been seared and fell radially outward in an area of about 30 kilometers in diameter. There was no clear evidence of a crater. In fact, the trees at ground zero were left standing upright, although they were completely stripped of branches and leaves. Because no significant meteorite samples were found, for many years scientists assumed that a small comet had exploded in the atmosphere. Recently, however, several teams of astronomers have argued that a small comet, composed of primarily light elements and ice, would break up too high above the ground to cause significant damage. They argue that the Tunguska explosion was actually caused by a small asteroid or large meteoroid traveling at supersonic speed. The Tunguska event is consistent with the explosion of an asteroid about 80 meters in diameter entering Earth's atmosphere at a shallow angle, moving at 79,000 kilometers per hour and exploding in the air as a result of it becoming exceedingly hot. The resulting shock wave slamming into the ground would cause the damage seen without creating a crater. The debate on the cause of the Tunguska event continues. On a typical clear night, you can expect to see a meteor about every 10 minutes. However, at predictable times throughout each year, Earth is inundated with them. These showers occur when Earth passes through the orbit of debris left behind by a comet. Although most meteors that enter Earth's atmosphere completely vaporize or are destroyed on impact, some land without totally disintegrating. Such pieces of debris are called meteorites, and they come from a variety of sources. By studying their chemistries and comparing them to the chemistries of planets, moons, asteroids, and comets, we know that meteorites were ejected from these bodies by collisions. For example, how SNC meteorites offer clues to the chemistry of Mars. By studying the chemistry and age of one meteorite from the moon that was found on Earth, geologists have determined that it was ejected into space when the Mare Imbrium impact basin formed. Meteorites from the asteroid Vesta show signs of having been molten rock on that world. They were ejected when an impact occurred there, creating a crater 460 kilometers wide and 13 kilometers deep, which has been seen from the Hubble Space Telescope. The spectra also reveal that some meteorites are debris that were never part of large bodies. Meteorites tell us the age of the solar system. Measuring the relative amount of various radioactive elements in them allows astronomers to determine how long ago they formed. The oldest known meteorites became solid bodies about 4.57 billion years ago, and impacts on Earth as early as 4 billion years ago have been identified based on how long they disturb pre-existing rock here. Therefore, the solar system is at least 4.57 billion years old, and we will use 4.6 billion years as its age in this book. People have been picking up debris from space for thousands of years. The description of meteorites in historical Indian, Islamic, Greek, and Roman literature shows that early people placed special significance on these rocks from heaven. Meteorites also have a practical impact, and falling space debris is increasing Earth's mass by nearly 300 tons per day on average. You can have stony meteorites, which are meteorites that mostly look like rocks that you might find in the surrounding area and are made out of rock. And you can also have iron meteorites, which look like very clean pieces of iron that you aren't necessarily going to see when you just look out into the desert around us. And you can also have stony iron meteorites, which look like a combination of the two. In the late 1970s, the geologist Walter Alvarez and his father, physicist Luis Alvarez, discovered the remnants of a truly earth-shaking impact. Working at a site of exposed marine limestone and the Apennine Mountains in Italy that had been on Earth's surface 65 million years ago, the Alvarez team discovered an exceptionally high abundance of iridium in a dark-colored layer of clay between the limestone strata. Recall from above that iridium was present on the surface of the Earth differentiated sank to the core. The iridium found by the Alvarez team had to have been deposited much later. Since 1979, when this discovery was announced, a comparable layer of iridium material has been uncovered at numerous sites around the world. In every case, geologic dating quickly reveals that this apparent worldwide iridium-rich layer was deposited about 65 million years ago. Paleontologists were quick to realize that the significance of this date because it was back then that all of the dinosaurs rather suddenly became extinct. In fact, 2/3 of all animal species disappeared within a brief span of time 65 million years ago. The Alvarez discovery supported an astronomical explanation for the dramatic extinction of so much life that once inhabited our planet, an asteroid impact. There is no universal agreement on the disasters that befell Earth during this episode. One scenario has an asteroid 10 kilometers in diameter slamming into Earth at high speed and throwing enough dust into the atmosphere to block out sunlight for several years. As the temperature dropped drastically and plants died for lack of sunshine, the dinosaurs would have perished along with many other creatures in the food chain that were highly dependent on vegetation. The dust eventually settled, depositing an iridium-rich layer over Earth. Another theory posits that the impact created enough heat to cause plant-wide fires, followed by changes in the ocean that killed many species of life on them. Whatever scenario turns out to be correct, small creatures capable of ferreting out seeds and nuts were among the animals that managed to survive, setting the stage for the rise of mammals and consequently the evolution of humans. In 1992, a team of geologists discovered that the hypothesized asteroid crashed into a site on the eastern edge of Mexico. They based this conclusion on glassy debris and violently shocked grains of rock ejected from the multi-ridge 195-kilometer diameter Chicxulub crater buried under the Yucatan Peninsula and western Caribbean Sea in Mexico. From the known rate at which radioactive potassium decays, scientists have pinpointed the date when the asteroid struck, 64.98 million years ago. In 1998, the geologists digging on the Pacific Ocean floor discovered a piece of meteoritic debris with precisely the same age, apparently a piece of the offending asteroid. By comparing the chemical composition of the debris in Chicxulub with the chemical composition of meteorites, astronomers and geologists in 2007 determined that the asteroid that caused the mass extinction 65 million years ago came from a group of asteroids called Baptistinus. The group was created as a result of a larger body, some 170 kilometers in diameter, breaking up after collisions 160 million years ago. The end of the dinosaurs' reign was not the only mass extinction caused by an impact. In 2001, evidence came to light concerning the Permian-Triassic boundary of 250 million years ago that suggests another devastating blow from space, this time called the Great Dying, a mass extinction during which 80% of the species of life living on land and 90% of those in the ocean perished. Rocks from that time discovered in places from Japan to Hungary show evidence in the form of fullerenes, soccer ball-shaped molecules containing at least 60 carbon atoms of an impact from space. Trapped inside these fullerenes were gases that could only have been forced into them by exploding stars. This signature of gas-filled fullerenes from space has now also been discovered in the layer of rock that existed on Earth's surface 65 million years ago. A 250 million-year-old crater that may have been relevant impact site was found in 2004 off the northwestern coast of modern-day Australia. Keep in mind that both this impact and the one that ended the reign of the dinosaurs occurred on a world whose surface is in continual motion. Therefore, their current locations are not the same as the initial impact sites. The Chicxulub impact actually occurred in the Pacific Ocean, whereas the Australian impact occurred before the continents were separated from Pangaea. This impact explanation of the Great Dying is not universally accepted. Another possible explanation is a massive amount of volcanic eruption that darkened the skies and changed the climate.